Welcome to GCP Shared VPC. Welcome to our comprehensive deep dive into Google Cloud Platform's Shared VPC solution. I'm excited to take you through this powerful networking feature that's absolutely essential for enterprise cloud architecture. Today we'll explore how Shared VPC enables centralized network management while maintaining project autonomy. Think of it as the networking backbone that lets different teams work independently while sharing common infrastructure securely. We'll cover everything from basic concepts to advanced implementation patterns, real-world use cases, and hands-on G-Cloud commands. By the end, you'll be ready to design and implement Shared VPC in your organization. This presentation follows a practical approach. Every concept comes with actual commands you can run, and I'll explain what each parameter does and why we use it. Understanding the problem. Before we dive into Shared VPC, let's understand why it exists. In traditional cloud setups, each project creates its own VPC network. This works fine for small organizations, but it creates serious challenges at scale. Imagine you're a large enterprise with multiple teams: development, staging, production, data analytics, and security teams. Each creates their own projects for isolation. But now you have problems. Overlapping IP ranges, duplicated firewall rules, complex inter-project communication, and no centralized network security. The networking team loses visibility and control. Developers can't easily connect to shared services like databases or monitoring systems. Security becomes a nightmare with dozens of separate networks to manage. This is exactly what Shared VPC solves. It provides centralized network management with distributed project autonomy. What is Shared VPC? Shared VPC is Google Cloud's solution for connecting resources across multiple projects using a single, centrally managed VPC network. Think of it as a hub-and-spoke model where one project owns the network infrastructure, and other projects can use it. The beauty is in the separation of concerns. The network administrators manage subnets, firewall rules, and routing in the host project. Application teams deploy their resources in service projects but use the shared network infrastructure. This diagram shows the core concept. One host project contains the VPC and subnets, while multiple service projects attach to it. Resources in service projects get IP addresses from the shared subnets but remain isolated at the project level for billing and access control. Notice how this enables both centralization and isolation, the best of both worlds for enterprise networking. Let's take a deep dive into the core components. Let's break down the essential components that make Shared VPC work. Understanding these is crucial for proper implementation. The host project is your network command center. It owns the VPC, subnets, firewall rules, and routes. Think of it as the networking team's domain. They control all network-level policies here. Service projects are where your application workloads live. They can use the shared network but can't modify it. This gives developers the networking they need without giving them network admin rights. The Shared VPC admin role is powerful. They can enable sharing and control which projects get access. This role should be carefully managed in your organization. Network users in service projects can create resources that use shared subnets. They can launch virtual machines, create load balancers, but can't change firewall rules or add subnets. Setting up your first Shared VPC. Now let's get hands-on. I'll show you how to enable Shared VPC step by step using G-Cloud commands. Every parameter here serves a specific purpose. First, we enable the Compute Engine API in our host project. The project flag specifies which project we're working with. This will become our network host. Next, we enable Shared VPC on the project. The Enable Host Project command transforms a regular project into a Shared VPC host. Notice we specify the exact project ID. This precision is crucial in multi-project environments. Then we create our Shared VPC network in subnet mode. The subnet mode parameter is important. It gives us fine-grained control over IP ranges per region, which is essential for enterprise networking. Finally, we create a subnet with a specific IP range. The CIDR block should be carefully planned to avoid conflicts with on-premises networks. Creating and managing subnets. Subnet creation in shared VPC requires strategic thinking. You are not just creating network segments. You are designing the foundation for multiple teams and applications. When we create subnets, the region parameter determines where resources can be deployed. The range parameter sets the IP address space. Choose this carefully, as changing it later is complex. The Enable Private IP Google Access flag is crucial for security. It allows virtual machines without external IPs to reach Google APIs and services. This is a security best practice that reduces your attack surface. Enable flow logs for network monitoring and troubleshooting. The aggregation interval controls how often logs are generated. Interval 5 SEC gives you near real-time visibility but generates more data. Secondary ranges are powerful for multi-service architectures. They are essential if you plan to run Kubernetes clusters, as pods and services need separate IP ranges. Attaching service projects. This is where the magic happens, connecting service projects to your shared network. The attachment process requires careful permission management. The associate project command links a service project to the host. Notice we specify both the host project and the service project explicitly. This creates the relationship that allows resource sharing. IAM binding is critical here. We're granting the compute network user role to service project owners. This role allows them to create resources that use shared subnets but doesn't give them network admin rights. The member parameter uses the project number, not the project ID. This is important. Project numbers are immutable and more secure for IAM bindings. Notice how we scope the binding to specific subnets. This gives you granular control. Different teams can access different network segments based on their needs. Understanding IAM in shared VPC is crucial because it controls access to your network resources. The permission model is designed around the principle of least privilege. The shared VPC admin role is the most powerful. It controls the entire shared VPC configuration. In most organizations, this should be limited to senior network administrators. Compute network user is the role most developers need. It allows them to create virtual machines and other compute resources that use shared subnets, but they cannot modify the network itself. Security admin can manage firewall rules across the shared network. This is often assigned to security teams who need to implement network security policies. Firewall rules in shared VPC. Firewall management in shared VPC is centralized, which is both powerful and requires careful planning. All rules are managed in the host project but apply to resources across all service projects. When creating firewall rules, the target tags parameter is crucial. Tags let you apply rules to specific groups of resources across multiple projects. Think of tags as your network security labels. The source ranges parameter defines where traffic can come from. Use specific ranges rather than 0.0.0.0/0 whenever possible. This follows the security principle of least privilege. Direction can be ingress or egress. Most rules are ingress, controlling what traffic can reach your resources. Egress rules control outbound traffic, useful for data loss prevention. The beauty of centralized firewall management is consistency. The same security policies apply across all projects using the shared network. Network security architecture. Security in shared VPC follows a layered approach. This diagram shows how different security controls work together to protect your infrastructure. At the network level, firewall rules provide the first line of defense. They are centrally managed in the host project, ensuring consistent security policies across all service projects. Identity and access management controls who can create and modify resources. The separation between network admins and resource users provides crucial security boundaries. Project-level isolation ensures that even though projects share network infrastructure, they maintain separate billing, access controls, and resource quotas. This multi-layered approach means a compromise in one area does not automatically compromise the entire system. It is defense in depth for cloud networking. Real-world use case. Multi-environment setup. Let me walk you through a realistic enterprise scenario. You have development, staging, and production environments, plus a shared services project for monitoring and databases. In this architecture, each environment gets its own subnet with appropriate IP ranges. Development might use 10.1.0.0 CIDR 24. Staging uses 10.2.0.0 CIDR 24. And production uses 10.3.0.0 CIDR 24. The shared services subnet, 10.0.0.0 CIDR 24, hosts resources that all environments need: monitoring systems, databases, CI/CD tools. This eliminates duplication and reduces costs. Firewall rules enforce environment isolation. Development can't directly access production, but all environments can reach shared services. This balances security with operational efficiency. This pattern scales beautifully. You can add new environments or services without redesigning your entire network architecture. Connecting to on-premises networks. Most enterprises need to connect their cloud networks to on-premises infrastructure. Shared VPC makes this much simpler because you have one network to connect instead of dozens. Cloud VPN provides encrypted connectivity over the internet. When setting up VPN, the peer IP is your on-premises public IP, and shared secret is the pre-shared key for authentication. The root parameter is crucial. It tells Google Cloud which on-premises networks are reachable through this VPN. Use specific ranges to avoid routing conflicts. Cloud Interconnect provides dedicated, high-bandwidth connections. It is more expensive but offers better performance and reliability for critical workloads. The beauty of shared VPC here is that once you establish connectivity, all service projects automatically inherit access to on-premises resources through the shared network. Monitoring and troubleshooting. Effective monitoring is essential for shared VPC because you're managing network infrastructure that multiple teams depend on. Let's explore the key monitoring capabilities. VPC flow logs capture network traffic metadata. They're invaluable for security analysis, performance troubleshooting, and cost optimization. Enable them on critical subnets. Firewall logs show which rules are being triggered. This helps you understand traffic patterns and optimize your security rules. Look for rules that are never used. They might be candidates for removal. Cloud monitoring provides dashboards for network metrics. Set up alerts for unusual traffic patterns, high latency, or connectivity issues. The centralized nature of shared VPC actually makes monitoring easier. You have one place to observe all network activity instead of monitoring dozens of separate VPC. Cost optimization strategies. Shared VPC can significantly reduce networking costs, but only if you implement it thoughtfully. Let me share some proven optimization strategies. Consolidating external IP addresses is a major cost saver. Instead of each project having its own NAT gateway, use a centralized NAT in the host project. This can save thousands of dollars monthly in large deployments. Shared load balancers reduce both costs and complexity. One global load balancer can route traffic to backends across multiple service projects, eliminating the need for per-project load balancers. Bandwidth costs are reduced because traffic between projects in the same shared VPC network stays within Google's infrastructure, avoiding external egress charges. The key insight is that sharing infrastructure resources almost always reduces total cost while improving management efficiency. Migration strategies. Migrating existing projects to shared VPC requires careful planning. You can't just flip a switch. It involves network redesign and potential downtime. The lift and shift approach recreates your existing network architecture in shared VPC. It's the safest migration path but doesn't optimize for the new model's benefits. Gradual migration involves moving one service or environment at a time. This reduces risk but requires maintaining parallel network infrastructures during transition. The key is thorough planning. Document your current network topology, identify dependencies, and create a detailed migration timeline. Always test in non-production environments first. Consider this an opportunity to optimize your network design, not just replicate what you had before. Common challenges and solutions. Every shared VPC implementation faces similar challenges. Learning from common pitfalls can save you significant time and effort. IP address planning is the most critical challenge. Overlapping ranges between on-premises and cloud, or between different cloud regions, create complex routing issues. Plan your IP addressing scheme before you start. Permission management gets complex with multiple teams and projects. Create clear role definitions and use groups rather than individual assignments. Document who has what access and why. Cross-project communication issues often arise from misconfigured firewall rules or missing IAM permissions. Always test connectivity between projects after setup. The solution to most problems is better planning and documentation. Shared VPC amplifies both good and bad network design decisions. Advanced patterns and best practices. Once you're comfortable with basic shared VPC, these advanced patterns can help you build more robust and scalable architectures. Multi-region shared VPC provides global networking with regional failover capabilities. Each region has its own subnets, but they are part of the same logical network. Hub and spoke with multiple hubs allows you to separate different types of workloads. You might have one hub for production workloads and another for development and testing. Hierarchical firewall rules use tags and service accounts to create layered security policies. This provides fine-grained control while maintaining centralized management. These patterns require more complex setup but provide enterprise-grade capabilities for large-scale deployments. Automation and infrastructure as code. Managing shared VPC manually does not scale. Let us explore how to automate your shared VPC deployment using infrastructure as code principles. Terraform is the most popular choice for Google Cloud infrastructure automation. It provides declarative configuration that is version controlled and repeatable. The Google Cloud Deployment Manager is Google's native IAC solution. It integrates tightly with other Google Cloud services and supports complex dependency management. Configuration management tools like Ansible can handle ongoing maintenance tasks such as updating firewall rules, managing IAM bindings, and monitoring configuration drift. The key benefit of automation is consistency. Every deployment follows the same patterns, reducing configuration errors and improving security posture. Security hardening checklist. Security should be built into your shared VPC design from day one. This checklist covers the essential security controls you should implement. Network segmentation using subnets and firewall rules creates security boundaries. Don't put everything in one large subnet. Separate workloads by function, environment, and security requirements. Least privilege access ensures users and services have only the minimum permissions they need. Regular access reviews help prevent permission creep over time. Logging and monitoring provide visibility into network activity. Enable VPC flow logs, firewall logs, and audit logs. Set up alerts for suspicious activity. Regular security assessments help identify configuration drift and potential vulnerabilities. Use tools like Cloud Security Command Center for continuous monitoring. Future-proofing your architecture. Technology evolves rapidly, and your shared VPC architecture should be designed to adapt. Let's discuss how to build for the future. Container and serverless adoption is accelerating. Ensure your network design supports Google Kubernetes Engine, Cloud Run, and other modern compute services. Multi-cloud strategies are becoming common. Design your network addressing and security policies to accommodate potential connections to other cloud providers. Zero-trust security models are replacing traditional perimeter-based security. Plan for identity-based access controls and microsegmentation. The key is building flexible, Modular architectures that can evolve with your organization's needs rather than requiring complete redesigns.